Let us continue our discussion on non-equilibrium thermodynamics. So we have learned that in the framework of non-equilibrium thermodynamics, the entropy change ds can be partitioned into two parts, that is ds exchange plus ds poured. And also we have seen that the total ds is greater than or equal to dq by t, which is nothing but the Clausius inequality. That's the partitioning of ds as a sum of ds exchange and ds prod is consistent with the second law of thermodynamics. Okay, so this is kind of a recapitulation of whatever we have discussed in our last class. We had actually gone to prove that this partitioning actually obeys the Clausius inequality. In turn, it obeys the second law of thermodynamics. So now today what we want to do, we want to establish that entropy is always produced in a spontaneous process. Okay, and we, as the spontaneous process, we take the example of irreversible flow of heat, which is a common spontaneous process in the universe where the heat flows from the region of higher temperature to the region of lower temperature. So taking this model system, we will see that entropy is always produced in a spontaneous process, that is S prod is greater than 0. So for that, the model we consider, the drawing of the model is here, where the system is isolated and the overall adiabatic jacket is put, and inside you can see there's a chamber, that is reservoir 1, which is this small chamber is the chamber 1, compartment 1, this small chamber is compartment 2, where this compartment 1 is encompassed by a big another compartment, which is the reservoir 1, and which keeps the compartment 1 at temperature T1, which basically keeps this temperature T1 of this small compartment with this big part of the reservoir at consistent isothermal condition of T1, and similarly here the overall temperature is maintained as T2, where del E Q1 is the heat exchanged from the reservoir 1 with the compartment 1, and del E Q2 is the heat exchanged with the reservoir 2 with the compartment 2, and delta I Q1 is the heat either given by compartment 1 to compartment 2 or heat accepted by compartment 1 from compartment 2, and similarly delta IQ2 is the heat either received or given to compartment 1. So let us consider the above diagram, which is a two compartment system. Each compartment is in equilibrium with a heat reservoir at different temperatures T1 and T2. These two compartments are separated from one another by a rigid heat conducting wall. The total change in the energy of compartment 1 is delta Q1, that is delta E plus Q1 plus delta I plus Q1, where delta E Q1 is the energy as heat exchanged with its reservoir, and delta I Q1 is the energy at heat exchanged with compartment 2. Similarly, for compartment 2, the relationship is delta Q2 equal to delta EQ2 plus delta IQ2. So essentially delta IQ1 equal to minus delta IQ2, because heat given up by the system by the compartment 1 must be the heat accepted by the compartment 2 and vice versa. That is, the heat rejected by compartment 1 is accepted by compartment 2 or vice versa. Okay. So this is the first page. So now we come to the second page as a continuation of this discussion, that is page number 2. So now each compartment is in equilibrium with its reservoir. So the temperature of the compartment 1 remains practically constant at T1 and compartment 2 remains at T2. Now let us establish some general thermodynamic relationship. So S can be taken as a function of internal energy U and the volume V. So ds equal to del U del S at constant V into du plus del S del V at constant U into del V into dV. So now, according to first law of thermodynamics, dq equal to du plus pdv, but at constant V del U by del q by del u at constant v equal to 1, because del v equal to 0 at constant v. So now in the overall process, as you can see from the diagram as shown, the walls are rigid, so the volume is not changing at all, so dv is constant. So both dv1 and dv2, they are individually 0. So ds equal to del s del u v plus du, because this dv is 0. That is equal, ds equal to 1 can be written as dq by t. So ds is replaced by dq by t, so it becomes 1 by t into dq by du v into dq del q del u v at constant v into du. So this del u v already you have found this to be 1. So this becomes, ds becomes du by t. So this du by t. So for compartment 1, ds1 equal to du by t1, and compartment 2, ds2 equal to du2 by t2. So here S, the total entropy, is equal to S1 plus S2, that is total entropy change, ds equal to ds1 plus ds2. So now we can replace this ds1 as du1 by t1 and ds2 by du2 by t2. So total ds becomes du1 by t1 plus du2 by t2. So here in the overall model, the v1 and v2 both are constant. So du1 in first law, according to first law of thermodynamics, du1 becomes dq1, because dv1 dv1 equal to 0. So d1 equal to dq1, that is delta eq1 plus delta iq1. So as dv1 equal to 0. Similarly for compartment 2, du2 equal to delta q2, that is de dq2 plus di dq2, as dv2 equal to 0, as already discussed. So now ds becomes du1 by t1 plus du2 by t2, that is this thing by t1 and this thing by t2, as expressed here, del e q1 by t1 plus del I q1 by t1, then del e q2 by t2 plus del I q2 by t2. So now we can write these two del e terms together and del I terms together. So that is equal to del e q1 by t1 plus del e q2 by t2 plus del I q1 by t1 plus del I q2 by t2. So del e, this is equal to del e q1 by t1 plus del e q2 by t2 plus del I q1 by t1 minus del I q1 plus t2, because already you have discussed that del I q1 equal to minus del I q2, because heat rejected by compartment 1 must be heat accepted by compartment 2 or vice versa. So del I q2 must be replaced, can be replaced by del I q1 minus del I q1. So the overall relationship becomes del S, which is nothing but del exchange plus ds prod, that is equal to del E q1 plus del by t1 plus del e q2 by t2 plus del I q1, you can take common, so it becomes 1 by t1 minus 1 by t2. So now one can easily distinguish that this thing is del E, del q1 by del e q2, that is the heat exchanged by compartment 1 from the reservoir 1, and this is the heat exchanged by the compartment 2 by with the reservoir 2. So naturally these two terms are nothing but ds exchange. The contribution to ds exchange can be separated easily. So this leftover becomes nothing but ds prod, overall ds prod in the whole system, both from the contribution from compartment 1 and compartment 2. So ds prod equal to del I q1 into 1 by t1 minus 1 by t2, that is del I q1 into t2 minus t1 by t1 t2. So this ds prod is the entropy produced in the two compartment system. Okay. So now we come to the third page of this discussion. This is page number 3. So let us take a closer look in the expression, that is ds prod equal to delta iq1 into t2 minus t1 by t1 t2. So the condition of ds prod is greater than equal to 0 implies that delta iq1 must be positive if t2 is greater than t1. That means if t2 is greater than t1, then this thing is positive, then this thing, if this is positive, the overall ds prod will become positive. So naturally this is so, if t2 is greater than t1, then heat flows from compartment 2 to compartment 1. So the heat accepted by compartment 1, that is del IQ1, will be positive, because the convention in thermodynamics that heat accepted by a system is positive and heat rejected by a system is negative. So this will be positive if T2 is greater than T1. So that means if this is greater than this one, T2 is greater than T1, del IQ1 becomes positive. Overall this is positive into positive, ds prod is positive for a spontaneous process. So physically this means that heat flows from compartment 2 to compartment 1 if T2 is T1, as heat accepted by a system is positive. Conversely, del IQ1 must be negative if T2 is less than T1. If opposite happens, T2 is less than T1, then this thing becomes negative, and in turn what will happen, that compartment 1 will reject energy, and heat energy rejected or reject heat rejected by a system, that will be negative. So this will be negative into negative, to overall it will be positive. So the heat flows from a compartment 1 to compartment 2 if T1 is T2. So this is our common sense. So heat flows from a region of lower temperature to the higher temperature, from the higher temperature to the lower temperature, and as a result the ds prod that always becomes positive for a spontaneous system. So thus the directionality of heat flow is dictated by the relation that ds prod is greater than or equal to 0, where the equal to sign is for the reversible system. Okay, so this equal to sign is for the reversible system. So for generality we keep it greater than or equal to 0, but this greater than sign holds good for the spontaneous system or non-equilibrium system. So on the other hand, the value of ds exchange is arbitrary, because we have partitioned as ds prod and ds exchange, and we have seen that the directionality of heat flow that is dependent upon only on ds prod, and ds exchange has no issue with that. Okay, so on the other hand, the value of ds exchange is arbitrary in the sense that it can be positive, negative or 0, and has nothing to do with the directionality of the heat flow. Okay, so this is a very important consequence. Thus the separation of ds into ds exchange and ds prod, that is ds equal to ds exchange plus ds prod, is fundamental. So that's the postulate we made in the last discussion. So we would eventually see that non-equilibrium thermodynamics is based upon the fact that ds prod is greater than 0 for non-equilibrium spontaneous irreversible processes. Okay, so this is the discussion I wanted to make today. So today what I'll give you all the copies of all these 3 pages. Okay, so now we have this discussion, this video also you have. So with that you can compare. This is your class note. So now I hope you will understand. So the subject I just wanted to discuss, and if you find any problem then you can get back, you can ask me questions. But just in brief, what we discussed, we have shown with the example of the irreversible flow of heat that the entropy is always produced in a spontaneous process, and we took the simplest possible example of non-equilibrium process, irreversible process or spontaneous process, which is the heat flow from the region of higher temperature to the region of lower temperature. That's the very common spontaneous process in nature. So with this example we have established the fact that ds prod is greater than 0 for all spontaneous processes, for these particular spontaneous processes, this particular spontaneous process. So later on we will take some more example and also show that ds prod is greater than 0 in that case also, and from that we can generalize the experience that ds prod is greater than 0 for all spontaneous processes. Thus one can conclude that the total entropy, that for any spontaneous process the total entropy change ds is greater than 0, but the overall ds is a huge quantity. You don't need to consider that. You can discard the ds exchange part, and only ds prod is greater than 0 will ensure that the system, the directionality of spontaneity. So I think with this I stop to this discussion. So next day we'll come back. Once you understand it, let me know your queries if at all, then only we'll put forward, we'll go ahead with the next part, where we'll discuss the once again the ds prod is greater than 0 for some other spontaneous process, so that from this result and from the result of the next class we can generalize that ds prod is in general greater than 0 or positive for any spontaneous process. So with this I close close today's discussion.